Alright guys, I'm going to do number 55. Alright guys, a commuter, so let's, train travels between two downtown stations because the stations are only 1 kilometer apart. The train never reaches its maximum cruising speed. During the rush hour, the train engineer minimizes the time interval change of t between two stations by accelerating for a time interval at delta t1. I'm not going to use the variables they use. I don't like to call it t1. I like to use my variables whatever I feel like. But the train is going to accelerate for a specific time at 0.1 meters per second. And then the and then it's going to decelerate, as we call it, at we don't really like to use that word, but that implies that you have acceleration with a negative value, or going in the opposite direction of its velocity. In other words, slowing down for a time interval of delta 2. Find the minimum time interval of travel in the time interval of dt. So basically what this is you have two train stations. You have two objects that are 1 kilometer apart. So this is going to be 1 kilometer. Or I'm going to call it x1, I guess. x1 is going to be 1 kilometer. And you have a train that's going to accelerate. It's going to pick up speed. Its velocity is going to increase. And then at some point, you want to decelerate right at that stop. And it wants us to find the time interval, delta t, between here and here, which I'm not going to use these variables, by the way. I'm going to just use my own variables. I don't care what anybody says. You guys can match them if you want, but personally, I just don't. There's no way in hell I'm going to start using them. I mean, you might as well call it delta x. I mean, if you're starting from 0 to x1, same thing with t. You could start t from 0. There's no reason to call it delta t, to be honest, but whatever. That's just me, though. Anyways, so, all right, let's off. Let's stop wasting time. I'm going to set up my graph here. In fact, I'm going to extend this a little bit. This is going to be the t-axis, and this is going to be the x-axis. So what this graph is going to look like is you're going to have a train that's going to start from rest. It's going to accelerate. And then once it accelerates, you're going to slow down. So you're going to travel a little extra distance, and it's going to slow down. This t1 is the time it takes for this to reach at the point. Actually, wait. That's not right. There we go. Okay, sorry for that. Yeah, so this is going to be t1. I have to slow down here. So this is going to be the t-axis, and this is going to be the x-axis. So it's going to accelerate at some point, which I'm going to call it t naught, I guess. And from t1, that's when it's going to travel to 1 kilometer. That's what x1 is. So x1 is going to be a specific value of 1 kilometer when the time it takes. So what we want to do, folks, is we want to maybe set up the equation right away. So let's do that. Let's say that x equals v naught, or a1 t1 or t square over 2 from the interval from 0 from t to t naught. That's what this first portion of the graph is. And then the other equation is going to have some initial position here, which I'm going to call it x naught, I guess. It's going to be some x naught value that it travels. And that x naught is going to be, a1 t naught square over 2. You can find that value. Added to some final velocity, which I guess I can call it v naught, I guess. Or I'm just going to call it straight up a1 t naught. That's going to be the final velocity. And that's going to be the new initial velocity over to the time interval from t minus t naught plus a over 2 over t minus t naught square over the interval from t naught to t all the way to until it reaches t1. So there's already the equation set up for you guys. The only unknowns that we don't know is going to be t naught and t1 and t, apparently. So those are the only two variables. We don't know what x naught is, so I really don't know how to solve this, or I guess the final velocity is 0 when it reaches its destination. So let's take the derivative, dx over dt of the second equation. And that's going to be 0. That's going to be t. So that's going to be a1 t naught over t minus t naught. Or actually, wait, that's not true. No, I'm almost right. So plus a over 2 times the 2 over t minus t naught. That's another way of the final velocity being the initial velocity, a1 t naught. This is going to be the initial velocity at that point. So that's going to be the v naught right there. Added to a over 2 over t minus t naught after the time interval from 0 to t to t1. And we're gonna stop it at t1. So we're gonna change the variable. So we're gonna call this x1, and we're gonna call this the time it takes t1 specifically for it to reach x naught, and that's the same time interval it takes for it to reach 0. So now already, folks, you already have your two equations, two unknowns. Use your rules of mathematics to solve for whatever these variables you have to, and get your t naught and t1 values, and you're done. That's all you need. Alright guys, I'm going to do a little extra step on these videos. I'm going to actually show the algebra steps. I'm not always going to do this, because looking at this, it looks like a mess. So this is solvable. Of course, it's just a matter of what technique is the easiest for us to use. And if you're perceptive, we don't have to solve for a specific single variable. So what I'm going to do is I'm going to isolate this variable, a1 t naught over a over 2. So I'm going to take this variable, move it over here, divide it by a2, and say that this is going to be t1 minus t naught. So notice that I am not solving for either of these. I'm solving for this specific one, this. And the reason for that is because I want this in terms to be into t naught, into one variable. So that's all I'm doing, folks. Notice that this is just, you have to find some technique that works. And this is going to, x naught is going to be a1 t, was it t naught squared over 2 plus a1 t naught, and this is where you're going to have to put parentheses, minus a1 t naught over a2. And this is where like being really pays off for folks. So I like to write every work so I can keep track of anything in case I make a mistake. So this square is just going to be this guy's square. So that's just going to be another way of saying a1 square t naught square over a2 square. There we go, folks. So once you get that done, we simplify this. So x1, I should probably pause this video here, but I'm going to keep going. T naught squared over 2. This is going to be minus a1 squared t naught squared over 2. And that looks like something cancels. Well, it doesn't really look like it cancels, but that's okay. And what is this? Plus a2, oh, actually, this simplifies. And actually, I think I messed up somewhere. I don't think I meant to write it. Yeah, I think I did mess up. I think that was supposed to be a2. Alright, hold on. Yeah, I did mess up. Okay, so this is going to be a2. So there we go. So a1 square, t naught square over a2. Okay, this is right. Okay, so this would be a1 square t naught square over 2 of the a2. And Wow, okay. So now you have x1 equals a1. They both have t naught squares. Oh my god. So you're not even going to use a quadratic formula on these ones. So I'm going to take this value, multiply by 1, so I can combine this variable, or this term here. So 2 and 2 times the invisible 1 here is going to be 2 minus a1 t naught square, both of these squares, over 2a2. I'm going to put a2 over a2. So I'm going to simplify this. So here you have a1, a2, t naught square, minus a1 square, t naught square, over 2a2. And I'm going to factor out the a1 and the t naught. So a1 is going to be out, so you'd be left with a2 minus a1. So factor out the a1, you'd be left with a2 minus a1, with the t naught being on the outside, over 2a2, and that's going to be x1 equals. So really, folks, all I'm doing is algebra work, and I'm not sure if I did this algebra right, but we will verify this regardless. So 2a1 over the a2 minus a1, and square root the thing, and that's going to be the time t naught. And remember, folks, all I'm solving for is one of the variables. Once you solve for one of the variables, once you solve for t naught, you can chug it in, and then you can solve for t1. And then you can use this one to solve for t1, and get all the values that you need, really. So once you solve for t naught, folks, you should get 129.10 seconds. And once you've solved for that, let's solve for t1 is. So all we have to do is take that a1 t naught divided by a2, add it to t naught, and that should get you t1, and that should get you the other value. All right, so once you get your other values, folks, you should get 154.92 seconds. And I guess we're done. So it's just a matter of reinterpret. All right, now since I got my values, let's kind of reinterpret this and write it in the format that they want. So during the rushing hour, the internal missile by time interval between two stations by starting for time interval t1 at that. Okay, so that's t1. Okay, so in this interpretation, the way I have it, this one is going to be 129.10 seconds. And that's going to be t naught in my case. And then immediately braking with acceleration for the time interval of d2. So that's really the difference between 154 point whatever the heck that is. So in this case, delta t2 in our case is going to be 25.82 seconds. And then the final solution, the whole delta t, which is what I call t1, is going to be 154.92 seconds. So I hope this helps.